Hello students, today we're going to talk about molecular geometries. My hope is that you have some information when you come into this video as it is, because the real goal for me is I want you to be able to better visualize the three-dimensional structure of these molecules and understand the names that we put behind them. That's a trigonal planar or a trigonal bipyramidal, something like that. And I also want you to be successful at drawing these three-dimensional structures on two-dimensional paper. So that's really the goal. I'm going to touch on all of these different geometries, and I'm going to do them in two videos. In the first one, I'm going to just focus on SP2 and SP3 hybridization of the central atom, which means that we are going to really need to understand this bonding pair business. So again, hopefully you have some familiarity with this, but a bonding pair is going to be a pair of electrons that is in between the central atom and some other atom hanging off of it, and so it is a bonded set of electrons. By the way, even a double bond will indeed be a single bonding pair, and I'll remind you of that. And then our non-bonding pairs, those are going to be lone pairs, as we would see from Lewis dot structures and things like that. And so if I only have three things hanging off of my central atom, even if one of those things is a lone pair, then I will have an electron cloud geometry that is trigonal planar, and that will bring with it a certain visual. And then I'll also talk about what happens when we have a total of four things hanging off of the central atom, where we get the tetrahedral shapes. The first example that I'm going to do is trigonal planar. So here's my formaldehyde molecule. Again, a reminder, even a double bond in here is going to be only considered as a single bonding pair. So I have 1, 2, 3 bonding pairs on this particular molecule. That means that it is going to be trigonal planar, because everything is trying to spread apart from one another as much as it possibly can, and it turns out this is as good as it gets. It's planar because, as you can see, I can actually put all of these different atoms into a single plane. That means if I want to draw it, it is particularly easy, because then I would just line it up so that everything is in the plane of the paper, and I can use solid lines when I'm drawing my bonds, and people will understand that that is still in the plane of the paper. I've just turned on a shell that's describing the electrons in the electron cloud, and you can see that here with this mesh. Always keep in mind that the electron cloud is significantly larger than any sort of ball and stick model we ever use, but this is still considered trigonal planar for the electron cloud as well. So even though it's very fat and bulgy on that plane, it's still more or less sticking out this way, and this way, so it is trigonal planar. From here, let's look at a bent molecule that is still SP2 hybridized, and so I'm going to now have a single non-bonding pair. My example for this is going to be SO2, sulfur dioxide. It does have another resonance structure that I am not showing, and also the double bonds are not being indicated on this at the moment. You will notice, though, that this is not a linear molecule. It is these oxygens are pushed down a little bit because there is a lone pair that is sitting up here. I can turn on the electron density so that you can see that a little bit. There is a little bit of an extra bulge up here. It's not actually really that much of an extra bulge. I think it's actually important to understand that when we draw the Lewis dot structures and we draw the little dots, and then we draw our lone pairs as this bubble with 2 dots in it, sometimes that gives you an idea that they are much larger than they actually are. The lone pairs are held fairly tight to the central atom itself. So there's the electron density, it's out here. It's not going to extend massively way out into here because it's that lone pair bubble. But it is out there, and so it is this lone pair that's out here that is repelling these groups over here, and these oxygens get pushed down a little bit so that, again, everything can spread. So again, a very simple and straightforward molecule to draw even on paper, because I will just make sure that the sulfur and the 2 oxygens align in the plane of the page, and then I can draw it, and I indicate my little bubble up here with the lone pair so that people understand that it's there. So for the electron cloud, which includes all of this mesh, we still call it trigonal planar. It's up here, it's down here, and it's down here. But if you only want to talk about these different atoms, then you just have these three that you're going to talk about, and it is a bent geometry. Okay, now they're going to get a little bit more interesting because we're going to have four things hanging off. So everything as the electron cloud is concerned is going to have a tetrahedral geometry. And what I'll do is I'll start with no lone pairs, and I'll just jump up one at a time. And we'll get into these different atomic geometries or molecular shapes. Okay, we start with methane, a very simple molecule. You can see this overall tetrahedral geometry. So whenever you have these four things hanging off, and they all spread out as much as they possibly can in three-dimensional space. So you'll notice these are not 90-degree angles. We're spreading in three-dimensional space. It is very symmetrical though. So if I line it up so you're looking down this bond right here, you can see that we have an even spread of these three hydrogens that are back there. And if I rotate this, so now we're looking at this guy, you can see it looks exactly the same. I'll rotate this one exactly the same and get the last one in there exactly the same. Highly symmetrical molecule. To draw this in 2 dimensions, my personal preference, what I like to do is I like to line up as much as I can in the plane of the paper. A plane being defined by 3 points means that I have to be able to get at least 3 of my atoms into the plane. And so I'm going to select these 3. You can see right now they're all in a plane, and then I'll rotate it a little bit here so that they're now in the plane of the paper. And you can see I have one other hydrogen that's coming out of the page and one that's going back behind the page. So that's where I use those wedges. So here, this solid wedge means coming out of the page, then the dashed wedge typically means going back behind the page. So you can get an idea here of this three-dimensional structure just from this drawing. Notice that I am not trying to show 90 degrees here. I'll actually try to truthfully show that it's larger than 90 degrees. There's a very common mistake I often see with this particular structure, and I'm going to show it to you so that you don't do it. This is impossible, what you see here. It has the pieces parts to it. It has a wedge that comes out, it has one that goes behind, and then it's got 2 solid lines indicating that they are in the plane. But this is impossible. Look at this carefully, and this is telling you that this hydrogen, that carbon, and this hydrogen are in the same line, so they are collinear. That is impossible. Looking at this molecule here, it is impossible for me to get any hydrogen in front of this carbon and have another one that's back behind it somewhere. It's just never going to happen. So even if I try to do something like this, where I line up, this one is actually coming out of the page a little bit right now, this one out of the page, that's behind and another behind. You cannot achieve what this drawing is attempting to show. So just keep that in mind. We'll just briefly look at the three-dimensional. You can see that it still has the electron cloud, still certainly has this tetrahedral geometry to it, which is also shared by the molecules and the atoms themselves. And certainly it's quite a bit more puffy than the ball and stick model would suggest. So now what we'll do is we'll move down and we'll get rid of one of our bonding pairs and we'll replace it with a lone pair. So that means we're moving one column to the right on the periodic table. So instead of carbon, we'll use nitrogen. Okay, so here's ammonia. You can see that if I look at it from this kind of top view, you can see that I still have this nice spread of my hydrogens, but notice they are all smushed down, just like I would expect from that overall tetrahedral geometry, because there is a lone pair that's sitting up here. And that lone pair needs room, and it's smushing everything else down. Drawing this can be pretty straightforward also. I usually, if you can, I think it's a good idea to put lone pairs in the plane of the paper because it's hard to draw them, in a wedge sort of fashion. So go ahead and take this thing that would be pointing straight up, and I'll kind of rotate it around so it's straight up here. Then there's my nitrogen, and then I would have another hydrogen, all those things in the plane of the page. And you can see that I have one wedge that's coming out and one that's going in. So we would call this as an atomic structure, or the molecular shape. We would say that this is trigonal because here's 1, 2, 3 things making up the base of a pyramid. So trigonal pyramidal. Here's the top of the pyramid itself. If I turn on the electron density here so that you can see that, you still see that there is a bulge up here because, again, of that lone pair. It has to be represented if you're going to talk about the overall geometry of the electron cloud, and so it is still tetrahedral in that case for the electron cloud. From here, we'll drop down to having two lone pairs and two bonding pairs. So certainly water is the most common example for this with a bent geometry. Here's my water molecule. You can see that again, these are not at a 90-degree angle. There are only 3 atoms. I must be able to make them in the same plane, which I'm showing here. And so I can turn this around, and keep in mind that overall it is still SP3 hybridized, so it has a tetrahedral electron cloud. That means that if I have these sitting here, then there's one that's coming up this way, one lone pair, and there's another lone pair that's going off that way. So as far as drawing this on two-dimensional paper goes, if I stick with my theme, this might look a little strange, but if I stick with my theme, I like to put those lone pairs in the plane of the page. So I would have one that's up right here and one that's going down right here, and I would show a hydrogen with a wedge coming out of the page and another one with the dashed wedge going back behind the page. And here it is with the electron cloud. So again, there's this bulge up here and a bulge here. You can see those things right here. There's the bulge, and there's another bulge over here. So that's one way that you could draw it. Alternatively, I don't think there's anything wrong with taking these 3 atoms, putting them all in the plane of the page, and now you have a lone pair that's coming out of the page a little bit, and you've got one that's going behind the page a little bit back there as well. And so whatever you can do to try to indicate to people that 3-dimensional geometry. As you can see, I chose to kind of draw some little rabbit ears on it so that that was clear. So again, bent geometry when it comes to just the atoms, and then tetrahedral geometry if I'm going to include my electron cloud. Okay, so I covered these different molecules here. Next, I can, in a separate video, go into the expanded octets. But as for this video, if everything was making sense to you, let your computer know.